There are two cities where you live. The one that you see, bathed in sunlight and familiar from the street, and another, far larger, that exists in a world of total and permanent darkness. A silent, second metropolis of immense, hollow rivers and vast hidden chambers, carved from the very rock and clay that holds our world aloft. It is a realm of impossible pressure and quiet, relentless engineering genius. A world that functions so perfectly, so silently, that you don't even know it is there. But how do we build these modern wonders? How do we conquer the most complex and dangerous construction site on the planet right beneath our own feet? Before we journey further, feel free to leave a comment with from what location you're watching this and what time it is there. Now, settle in as our exploration truly begins. The great and ever-growing cities of our modern world are now confronting a fundamental and inescapable limit. For centuries, our solution to growth was to expand outwards across the land and upwards into the sky. But the surface of our urban centers has now become a finite and precious resource, a landscape so crowded, so congested, and so saturated with the infrastructure of our success that there is simply no more room to build. The great arteries of the city, its roads and its railways, are choked to grow, to thrive, to even survive. The city must now evolve in a new and radical direction. It must create an entirely new layer of existence, a deeper and more efficient circulatory system, far below the chaos of the surface. This is the great and defining engineering imperative of our time, a push into a new frontier that is not in some distant land, but is buried just a few meters beneath the soles of our shoes. This subterranean frontier, however, is not an empty and welcoming void. The ground beneath any major city is a dense, chaotic, and almost geological jungle of our own making. It is a three-dimensional labyrinth, a compressed and tangled history of all the generations that came before. Here lie the immense and often poorly documented concrete foundations of the skyscrapers that anchor the world above. Here are the crumbling and fragile brick sewers of a bygone industrial age, the forgotten pneumatic tubes, and the ghostly abandoned passages of failed transit systems. Woven through this ancient and man-made debris is the critical and incredibly sensitive nervous system of the modern city, the colossal high-pressure water mains, the explosive gas lines, and the vast, delicate, and indispensable bundles of fiber optic cables upon which our entire digital world depends. To drive a new passage through this environment is to perform a kind of blind, high-stakes surgery, where a single millimeter-level error could be catastrophic. To meet this immense and almost impossible challenge, modern engineers have perfected two primary and profoundly different philosophies for creating these new subterranean worlds. The first is the philosophy of the unyielding forward advance. This is the domain of the tunnel boring machine, the great cylindrical mobile factory that grinds its way through the earth in a single, relentless, and continuous push, creating a perfect circular artery as it goes. It is the strategy of overwhelming the earth with a masterpiece of mechanical power. The second and more subtle philosophy is that of the patient observational dance. This is the world of the sequential excavation method, a technique that is less like a drill and more like the work of a sculptor with a chisel. It is a cyclical and adaptive process of revealing and supporting the ground in small, manageable increments. A method that is used to create the complex, the bespoke, and the often immense open shapes of our deepest and most ambitious subway station caverns. Before either of these great and powerful methods can be deployed, however, before the first ton of earth is ever disturbed and before the first detailed blueprint is ever finalized, the engineers must first obey the single, great, and unbreachable commandment of all subterranean construction. They must first see the invisible. They must create a perfect, a flawless, and a high-resolution map of the unseen world that they intend to invade. They must chart its hidden and shifting layers of clay, of gravel, and of solid rock. They must locate its secret underground rivers and its pockets of high-pressure water, and they must identify and plot the precise location of every single one of its forgotten, man-made obstacles. This is the silent, the painstaking, and the absolutely critical science of geotechnical investigation. And it is here that our deep and our detailed journey into the heart of the modern underworld must now truly begin. To build in the hostile and crushing darkness of the deep ocean requires a level of foreknowledge that is almost absolute. On land, a construction site is a known quantity. We can walk it, we can see it, we can test it with relative ease, but the deep seabed is a world that is forever denied to our direct senses. It is a battlefield that must be surveyed and understood with a perfect, almost godlike vision before the first piece of steel is ever designed and before the first plan is ever drawn. The first great act of all offshore engineering, therefore, is a mission of pure exploration, a high-technology voyage of discovery. It is the painstaking and multi-layered process of creating a perfect, a precise, and a high-resolution three-dimensional map of a completely alien world, a task that must be performed from the deck of a survey vessel, floating on the turbulent surface, many kilometers above the silent landscape that it is trying to see. The first layer of this great invisible map is the shape of the abyss itself. This is the science of bathymetry, and it is achieved with a remarkable tool known as a multi-beam echo sounder. Mounted to the hull of a specialized survey vessel, this instrument does not just send a single, simple ping of sound to the bottom, as the echo sounders of the past did. Instead, it emits a wide, fan-shaped pulse of acoustic energy, a swath of sound that can be hundreds of meters wide. As this fan of sound travels through the water and strikes the seabed, it is reflected back. The echo sounder's incredibly sensitive receivers then listen for the thousands of individual return echoes from within that single pulse. By measuring the precise split-second travel time of each of these thousands of echoes, a powerful computer can instantly calculate the exact depth and position of each point on the seabed that the sound has touched. As the survey vessel moves in a slow, methodical, grid-like pattern known as mowing the lawn, it is in effect painting the unseen ocean floor with sound, stroke by overlapping stroke, revealing for the very first time the true and complex topography of the hidden world below, its hidden mountains, its sweeping plains, its ancient submerged river channels, and its deep, winding canyons. To know the shape of the seabed, however, is not enough. The engineers must also know what lies directly beneath its skin. They must understand the shallow geology, the layers of sediment and of rock that make up the upper crust of the ocean floor. To achieve this, a second and more powerful acoustic tool is used, the sub-bottom profiler. This instrument works on a similar principle to the echo sounder, but it uses a much lower frequency and a much more powerful pulse of sound. This low-frequency sound is capable of penetrating through the soft upper layers of mud and silt on the seabed. As this pulse of energy travels down into the earth, a portion of its signal is reflected back every time it strikes a new geological layer with a different density. The boundary between a layer of soft clay and a harder layer of dense sand, for example, or the transition from the ancient sediments to the solid bedrock far below. By listening for this complex, layered sequence of deeper echoes, geophysicists can create a two-dimensional, cross-sectional image of the geological strata beneath the ship's path. It is a form of geological ultrasound, an acoustic MRI, that allows the engineers to see a ghostly but invaluable image of the unseen history and the structural makeup of the ground they intend to build upon. With the shape of the world and its underlying geology now beginning to come into focus, the next task is to meticulously scan the surface of the seabed for any potential hazards. For this, a third acoustic instrument is deployed, the side scan sonar. This device is often housed in a hydrodynamic, torpedo-shaped vehicle known as a towfish, which is connected to the survey vessel by a long armored cable and is towed behind the ship, flying at a controlled altitude just above the ocean floor. From this towfish, two very high-frequency fan-shaped beams of sound are sent out, not down, but to the sides. The system then records the intensity of the echoes that are reflected back from the seabed. Hard, rocky surfaces and man-made objects will reflect a strong signal, which is displayed as a light patch, while soft muds and silts and the shadows cast by any raised objects will reflect a weak signal, which is displayed as a dark patch. The result is a stunningly detailed, black and white, almost photographic image of the texture of the seabed and of any and all objects that are lying upon it. This is the tool that is used to find and to map the dangerous and unexpected, the wrecks of ancient ships, the unexploded ordnance from forgotten wars, the colossal glacier-dropped boulders, or the existing and vitally important pipelines and communication cables from previous offshore projects. This complete but still indirect acoustic picture of the seabed must then be verified by a final and absolutely essential act of physical confirmation. This is the geotechnical investigation, the moment when we finally get to touch and to sample the ground itself. For this, a much larger and more specialized drilling vessel is brought to the site. At precise, predetermined locations, a drill string is lowered to the seabed, and a hollow steel tube is driven deep into the ocean floor to extract a physical cylindrical core of the soil and the rock. These cores are then brought back to the surface, where they are carefully logged, sealed, and sent back to a laboratory on shore for a battery of tests to determine their precise physical properties. In conjunction with this, a technique known as cone penetration testing, or CPT, is often used. In this process, a large, heavy, and instrument-laden cone-shaped probe is pushed from the drilling vessel deep into the seabed. As the cone advances, its sensors send back a continuous, real-time stream of data on the soil's strength, its density, and its frictional properties. This is the ground truth mission, the final crucial step that provides the engineers with the hard physical data that they need to design their foundations with confidence. The final result of this long, expensive, and multifaceted campaign of exploration is the creation of a single, unified, and immensely complex document, the integrated ground model, all of the different and disparate streams of data that have been collected, the high-resolution bathymetry from the multi-beam echo sounder, the geological cross-sections from the sub-bottom profiler, the photographic imagery from the side-scan sonar, and the hard physical data from the dozens of core samples and cone penetration tests are all brought together and fed into a powerful, three-dimensional geospatial software package. The result is a complete and interactive digital twin of the unseen construction site. It is a virtual world that the engineers can now fly through, a world where they can see the precise shape and texture of the seabed, where they can peel back the upper layers of sediment to see the underlying geology, and where they can examine the precise soil strength at the exact location of every single foundation pile. This model is the ultimate map, the final and definitive intelligence report on the alien world below. But the ground, for all its complexity, is only half of the battlefield. The engineers must also have a deep and predictive understanding of the immense and powerful body of water that the structure will have to live in for its entire life. This is the world of meta-ocean studies, a specialized discipline that combines meteorology and oceanography. For a period of at least a full year before the final design is approved, a series of instrumented buoys and subsea sensor packages are deployed at the construction site. These instruments maintain a constant 24-hour-a-day vigil, collecting a continuous stream of data on every aspect of the ocean's behavior. The speed and direction of the surface and subsea currents, the height and frequency of the waves, the patterns of the tides, and the speed and direction of the winds. The goal of this long study is not just to understand the average day-to-day conditions, but to build a statistical model that can accurately predict the most extreme and violent conditions the structure will ever have to face. The brutal and singular 100-year storm that is the ultimate and defining test of its strength and survival. With this complete and almost godlike vision of the unseen world now finally assembled, a perfect and multi-layered map of the seabed, a deep and physically verified understanding of the geology that lies beneath it, and a powerful, predictive model of the ocean's own, often violent behavior. The quiet war of intelligence is over, and the true work of design and of construction can, at long last, begin. Armed with this immense and powerful library of knowledge, the engineers are now finally ready to choose and to deploy their first, their most iconic, and their most powerful of the great philosophies of offshore construction, the philosophy of the fortress. How then do you fabricate on dry land a colossal open lattice steel structure, a jacketed tower that can be taller than the Eiffel Tower, and then undertake the almost unbelievable task of transporting it for hundreds of kilometers out into the open sea, and then deliberately, and with a perfect and breathtaking precision, sink it, to stand for an eternity on the silent and now perfectly understood floor of the ocean. With a perfect and multi-layered understanding of the unseen world now in hand, the great work of building can, at long last, begin. The engineers, armed with their precise maps of the seabed and their deep knowledge of the ocean's power, are now ready to unleash their first and most iconic of solutions, the philosophy of the fortress. This is the strategy of absolute and uncompromising resistance. It is a declaration of war against the sea, a decision to meet the ocean's immense and chaotic power with an even greater and more intelligently directed human strength. The goal is not to evade and not to flex, but to stand firm. This philosophy is embodied in the classic and still ubiquitous offshore oil and gas platform, the fixed jacket platform, a colossal open lattice tower of steel, a man-made island that is designed to stand immovable and defiant in the face of the most powerful storms the planet can produce. The life of this steel giant begins not in the ocean, but in a vast, sprawling, and highly specialized construction yard on the coast. These fabrication yards are immense, open-air factories, where the raw steel for the platform is transformed into a single, colossal, and integrated structure. The primary component of the platform, its great legs and its supporting frame, is known as the jacket. This is a massive three-dimensional truss of enormous, hollow steel tubes, all meticulously cut, shaped, and then welded together with a level of precision that is almost absolute. A single large jacket can be a structure taller than the Eiffel Tower, and can contain more steel than 20,000 cars. Its design is a masterpiece of structural efficiency, an open lattice that is designed to be incredibly strong, while presenting the smallest possible profile to the immense pushing forces of the ocean's waves and currents. For months, or even years, this great steel skeleton is painstakingly assembled on its side, in a slow and deliberate ballet of heavy lifting, of precise alignment, and of the brilliant white light of the welder's torch. Once this colossal steel tower, this jacket, is fully assembled, it must then embark on one of the most remarkable and precarious journeys in all of modern construction. It must be moved from the dry land of its birth out into the open ocean to its final and permanent home. The first step in this journey is the loadout. The entire multi-thousand-ton jacket must be slowly and with incredible care skidded from its construction supports onto a massive semi-submersible barge, a specialized ocean-going vessel that is, in itself, an immense and impressive piece of engineering. Once the jacket is securely fastened to the deck of this barge, a process known as the sea fastening, the flotilla begins its long and slow journey out to sea. A team of powerful tugboats will tow the barge, with its colossal and precious cargo, for hundreds of kilometers across the open ocean. A journey that is minutely planned to take advantage of the calmest possible weather. Windows, as the entire project is incredibly vulnerable during this transitional phase. The arrival of the flotilla at the designated offshore location marks the beginning of the most dramatic, the most dangerous, and the most breathtaking phase of the entire operation: the launch and the upending of the jacket. The great semi-submersible barge is first carefully ballasted, allowing it to partially sink into the water. Then, with all of the support vessels standing at a safe distance, the sea fastenings that have held the jacket to the deck of the barge are cut away. With a deep and thunderous groan of protesting steel, the colossal jacket, under its own immense weight, begins to slide off the tilted deck of the barge and into the sea, in a controlled, but nonetheless spectacular splashdown. But the jacket is not yet in its final position. It is now floating horizontally in the water, a massive, lattice-like tube of steel. The final step is the upending, by selectively and remotely flooding the hollow legs of the jacket with seawater. In a precise and carefully calculated sequence, the engineers can cause one end of the jacket to become heavier than the other. In a slow, graceful, and perfectly controlled rotation, the great jacket then pivots from its horizontal floating position into a vertical one, until its lower legs make their first soft and gentle contact with the seabed, hundreds of meters below. With the colossal steel jacket now standing under its own immense weight on the ocean floor, its position monitored and confirmed to be within a few centimeters of its intended target, the next and absolutely critical phase of the installation begins. The jacket is not yet a fortress. It is merely a colossal and very heavy piece of steel, resting on the soft mud of the seabed. It must now be permanently and unshakably anchored to the planet itself. This is the task of the pile foundation, a process that must be carried out by a specialized, heavy-lift construction vessel. This vessel will lift immensely long, hollow steel piles, each of which can be hundreds of meters long and several meters in diameter, and will lower them down through a series of special guides, the pile sleeves that were built into the corners of the jacket. Under their own immense weight, these piles will plunge deep into the soft sediments of the seabed. But the weight of these piles alone is not enough to provide the required strength. They must be driven deep into the firmer and more stable soils that lie far below the mudline. To achieve this, a colossal and almost unbelievably powerful machine is used, the hydraulic hammer. This is a massive percussive device which is lowered from the construction vessel and is placed on top of a pile. It works like a giant automated sledgehammer, using a series of powerful hydraulic rams to lift and then to drop an immense steel weight, the ram, onto the head of the pile again and again and again. With each thunderous and bone-jarring blow, the pile is driven a few more centimeters into the resistant earth. This process is repeated for every single one of the piles, a slow, loud, and brutal process of forcing the deep roots of the platform into the seabed, until they have reached their final, calculated depth, a depth at which they have generated enough skin friction with the surrounding soil to anchor the platform against the most powerful storms that the ocean can ever produce. with the jacket now firmly and permanently pinned to the seabed. The final pieces of the great steel island can be assembled. The very last components to be installed are the topsides. These are the large, integrated, and modular decks that contain the drilling equipment, the processing facilities, the power generation plant, and the living quarters for the 100 or more people who will live and work on this remote man-made outpost. These topside modules are colossal and incredibly heavy structures in their own right, often weighing thousands or even tens of thousands of tons. They are fabricated and fully outfitted on land, and are then carried out to the site on another barge. The final installation is then performed by one of the largest and most powerful machines on the planet, a heavy-lift crane vessel. In a single, colossal, and incredibly precise lift, the crane will pick up the entire multi-thousand-ton topside module and will carefully, and with a precision of only a few millimeters, lower it onto the top of the waiting jacket, where it is then welded into place, the final and crowning act in the creation of the great steel fortress. This great and now fully assembled steel island stands as a profound and powerful testament to the philosophy of brute force resistance. It is a structure that has been designed with an immense factor of safety to be stronger than any conceivable force that the ocean can throw at it. But this philosophy has its limits. As the search for oil and gas pushes us into ever deeper and more hostile waters, a point is reached where a fixed steel jacket platform, a structure that must extend all the way from the seabed to the surface, simply becomes too large, too heavy, and too expensive to be a viable solution. In these deeper waters, the fortress must evolve. It must take on a new and even more colossal form, one that is not made of a slender lattice of steel, but of a solid and almost unimaginable mountain of pure reinforced concrete. The fixed steel jacket platform is a masterpiece of structural efficiency, a powerful and elegant solution for conquering the continental shelf. But as the relentless quest for energy pushes humanity into ever deeper and more hostile waters, a point is reached where the sheer length and weight of the required steel jacket becomes a profound and almost insurmountable challenge. The fortress philosophy, the strategy of brute force resistance, had to evolve. It needed to take on a new and even more colossal and a more monolithic form. The solution was to abandon the slender, open lattice of steel, and to instead build a literal mountain. This is the world of the gravity-based structure, or GBS, a colossal behemoth of reinforced concrete, a structure so unimaginably heavy that it does not need to be pinned to the seabed with piles. It is designed to simply, and with an almost unimaginable inertia, sit on the ocean floor, and to resist the most powerful and violent storms on the planet through its own sheer and monumental dead weight alone. The very existence of such a structure is entirely dependent on the unique geological and marine environment of its birthplace. Unlike a steel jacket, which is assembled from many smaller parts, a concrete gravity-based structure is a single continuous and monolithic entity, and it must be built in a very specific way. Its life begins in the calm, deep, and protected waters of a coastal fjord, most famously, along the dramatic and fjord-carved coastline of Norway. Here, a temporary and massive dry dock is first constructed at the water's edge. In this dry dock, the very base of the great structure is cast. This often includes a series of massive, hollow concrete storage cells which will later be used to store crude oil, and a set of deep, sharp concrete or steel skirts that will form the foundation of the structure. This is the most conventional part of the construction, a process of building a colossal, reinforced concrete base on dry land. Once this immense concrete base has been fully constructed and has cured to its full strength, the first of many engineering miracles occurs. the great sea gates of the dry dock are opened, and the basin is slowly and deliberately flooded. The partially built structure, now with its base complete, has been designed with just enough hollow volume to become buoyant. It lifts gently from its foundations and becomes a massive, floating, concrete island. It is then towed by a team of tugboats from the shallow dry dock out into the deep still waters of the fjord, where it is securely moored. This floating and now deeply submerged concrete base now becomes the foundation for a new and almost surreal kind of vertical factory. The construction of the platform's colossal hollow concrete legs now begins, using a remarkable technique known as continuous slip forming. For 24 hours a day, 7 days a week, a single ring-shaped formwork is slowly and constantly jacked upwards, while a never-ending river of fresh concrete is poured into it, and a dense curtain of steel reinforcement is fed into the walls. The great concrete legs of the platform literally grow towards the sky, while the entire ever heavier structure simultaneously sinks deeper and deeper into the calm waters of the fjord. While this immense concrete substructure is growing in the water, its other half, the topsides, is being constructed simultaneously on land. The topside deck is the operational heart of the platform, a massive integrated structure weighing tens of thousands of tons, which contains all of the drilling equipment, the processing facilities, and the living quarters. Once both the concrete legs and the topside deck are complete, they must be brought together in one of the most spectacular and nerve-wracking operations in all of marine engineering, the deck mating. The colossal steel topside deck is loaded onto a pair of specially designed barges. This deck-laden flotilla is then carefully and with microscopic precision maneuvered into the fjord and positioned directly over the top of the mostly submerged and waiting concrete legs. Then the final delicate ballet begins. The ballast water is slowly and carefully pumped out of the hollow legs of the concrete structure. As its buoyancy increases, the entire million-ton concrete behemoth begins to slowly rise. It rises with a perfect and unwavering control until it makes gentle and perfect contact with the underside of the deck, lifting the entire colossal structure clean off of its transport barges and taking its full immense weight for the very first time. The great concrete mountain is now fully assembled, a single colossal and integrated entity, floating serenely in the calm, protected waters of the fjord. But its final home is hundreds of kilometers away, in the violent and unpredictable waters of the open ocean, and so it must now embark on its final and most majestic journey. The towing of a completed gravity-based structure is a global headline-making event. An immense flotilla of the world's most powerful ocean-going tugboats is assembled. The largest and most famous of these journeys was that of the Troll, a gas platform in 1996. The entire 472-meter-tall, 1.2 million-ton structure was towed for 11 days on a slow and majestic procession out of the Norwegian fjord and across the North Sea. It was, and it remains, the tallest and heaviest object that has ever been successfully moved by mankind. The sheer, almost unbelievable power and coordination that is required to pull, to steer, and to control an object of such almost geological scale is a profound and humbling testament to the power of modern naval engineering. Upon its arrival at its final and precisely pre-surveyed deep water location, the last great act of the platform's creation begins. Its final descent, the installation of a gravity-based structure, is in principle remarkably simple. It must be deliberately, and with an almost perfect control, sunk. The process begins by opening a series of massive sea valves, allowing the seawater to begin flooding the immense, hollow concrete legs and the storage cells at its base. This is not a fast or violent process. It is a slow, meticulous, and perfectly orchestrated descent that can take several days to complete. A team of engineers using a suite of powerful computer-controlled pumps and valves and guided by a constant stream of data from both satellite-based GPS systems and a network of subsea acoustic positioning transponders can control the descent with a precision of mere centimeters. They are, in effect, landing a skyscraper on a precise, unseen target, on the seabed, 300 meters below the waves. The final moments of this descent are the most critical. As the structure nears the seabed, the deep concrete or steel skirts that form its foundation make their first contact with the soft upper layers of mud and silt. As the last of the ballast water is brought in, the full 1.2 million ton weight of the structure settles onto the seabed, and these skirts are designed to penetrate several meters into the soft clay, providing a powerful lateral stability and preventing any future erosion or scour from the ocean's currents from undermining the foundation. The final microscopic voids that may remain between the flat base of the structure and the slightly uneven seabed are then filled by pumping a specialized high-strength grout mixture under the platform. This ensures that the colossal weight of the structure is perfectly and evenly distributed over the entire foundation area. The Great Concrete Mountain is now a permanent and unshakable new feature of the ocean floor, a man-made island of pure, immovable mass. The colossal and almost unbelievably massive concrete gravity-based structure represents the absolute and undisputed zenith of the fortress philosophy of offshore engineering. It is a man-made mountain, a structure that is designed to meet the awesome and chaotic power of the ocean with its own, even greater and more profound sense of permanence and inertia. But this entire philosophy, for all of its brute force power and its undeniable success, has a fundamental and an unbreachable limit: the depth of the water. As our relentless quest for the world's resources continues to push us ever further from the familiar territory of the continental shelf and out into the truly and profoundly deep waters of the open ocean, a point is inevitably reached where building a single continuous structure that extends all the way from the seabed to the surface is no longer physically or economically possible. The fortress in all its forms must finally be abandoned. A new, a more subtle, and a far more radical philosophy is required. How then do you build a platform that does not try to fight the immense and powerful forces of the ocean, but has instead been taught how to gracefully and perpetually dance with them? The great bottom-founded fortresses of steel and of concrete are a magnificent and powerful solution to the challenge of the sea, but they are a solution that is ultimately bound by a fundamental and an unbreachable limit: the depth of the water. As our relentless search for the world's resources continues to push us ever further from the familiar shallow territory of the continental shelf and out into the truly and profoundly deep waters of the open ocean, a point is inevitably and quickly reached where the very idea of building a single continuous structure that extends all the way from the seabed to the surface becomes a physical and an economic impossibility. The philosophy of the fortress, the strategy of brute force resistance, must finally be abandoned. A new, a more subtle, and a far more radical philosophy is required. This is the philosophy of the dancer, a strategy that is born from a deep and a humble respect for the immense and untamable power of the deep ocean. It is a philosophy that seeks not to fight the great forces of the sea, but to gracefully and perpetually dance with them. The most common and the most recognizable of these great deep water dancers is the semi-submersible platform. This is a unique and brilliantly ingenious design that achieves its profound stability by hiding the vast majority of its mass and its buoyancy in the calm, quiet, and undisturbed waters far below the violent chaos of the surface. A semi-submersible consists of a large operational topside deck, which is supported high above the water by a series of massive, hollow, vertical columns. These columns are in turn connected at their base to two large submarine-like pontoons or hulls, which are completely submerged deep beneath the waves. The key to this design is that the slender vertical columns are the only part of the structure that must pass through the high-energy wave action zone at the surface. They are designed to present the smallest possible profile to the waves, allowing the violent energy of the sea to pass by them with minimal effect. The great buoyant pontoons, which provide the vast majority of the platform's stability, are so deep that they are almost completely unaffected by the storms that rage on the surface, creating an incredibly stable and solid working platform, a floating island that remains remarkably still while the sea heaves and pitches around it. A second and increasingly prevalent member of this family of deep-water dancers is the floating production, storage, and offloading vessel, more commonly known as the FPSO. This is a colossal and all-in-one floating factory, a machine that takes the form of a massive purpose-built or converted supertanker. The genius of the FPSO lies in its integration of all the necessary functions into a single, mobile vessel. It has the processing equipment on its deck to separate the oil, the gas, and the water that comes up from the seabed. It has the immense and built-in storage capacity of its own great hull to store the processed crude oil, and it has the ability to periodically and directly offload that stored oil to a smaller conventional shuttle tanker that moors alongside it, a process that completely eliminates the need for a multi-billion-dollar and often environmentally risky pipeline to the shore. The FPSO is typically anchored to the seabed by a single, complex, and incredibly robust mooring system that is connected to a great rotating turret, which is integrated into the vessel's hull. This allows the entire colossal ship-shaped platform to slowly and passively weather vane, always turning its bow into the prevailing wind, waves, and currents, a feature that dramatically reduces the environmental forces on the vessel and its mooring system. A different and beautifully elegant solution to the problem of stability is the spar platform. The spar is a unique and deeply impressive structure that takes its inspiration from a simple, floating fishing bobber. It consists of a single colossal and deeply drafting vertical cylinder, which can be over 200 meters long and 30 meters in diameter. This great hollow cylinder is heavily ballasted at its bottom, which places its center of gravity far, far below its center of buoyancy. This makes the spar incredibly stable and almost completely immune to the pitching and rolling motions of the sea. It floats in the water like a giant vertical needle, with the vast majority of its length submerged in the calm, deep waters and only a small portion of it visible on the surface, upon which the topside deck is mounted. The earliest spars were built with a single, massive enclosed cylinder for their hull, but the design has since evolved into the more efficient truss spar, which uses a lighter and more hydrodynamically transparent open truss structure for its midsection, a design that further reduces the effect of the powerful, deep-water ocean currents. Perhaps the most complex and the most unusual of all the great deep-water dancers is the tension leg platform, or the TLP. This is a structure that achieves its profound stability not through its shape, but through a constant and powerful battle between buoyancy and a set of taut vertical tethers. A TLP consists of a floating, semi-submersible-like structure, which is designed with so much buoyancy that it wants to float much higher in the water than its final operational position. This immense upward-pulling, buoyant force is then counteracted by a series of incredibly strong and completely vertical steel pipes or tethers that connect the corners of the platform to a secure foundation on the seabed. These tethers are pulled into a state of immense and constant tension by the platform's own desire to float upwards. They are, in effect, as taut as a set of colossal deep-water guitar strings. This constant high tension makes the platform almost completely immovable in the vertical direction. It cannot heave up and down with the waves. It can, however, shift slightly from side to side, and it is this unique combination of vertical rigidity and horizontal compliance that makes the TLP one of the most stable, and also one of the most complex floating production systems ever conceived. A floating platform, for all its grace and stability, is utterly useless if it cannot maintain a safe and continuous connection to the wellheads that are located on the seabed, often 2 or 3 kilometers directly beneath it. This connection is the job of the riser, the true and unsung hero of all deep water production. The riser is the platform's flexible and immensely long umbilical cord. It is a system of pipes that must be strong enough to withstand the immense pressures of the deep, yet flexible enough to accommodate the constant and complex three-dimensional movement of the dancing platform on the surface. The design of these riser systems is one of the most challenging and sophisticated disciplines in all of offshore engineering. They are a complex assembly of high-strength steel pipes, of flexible, articulated joints, and of buoyant, foam-like modules that help to support the riser's immense weight in the water. And on the platform itself, the risers are connected to a series of powerful hydraulic tensioning systems, which are constantly and automatically adjusting to the heaving, pitching, and rolling of the platform, ensuring that these vital and irreplaceable deep-water arteries are never bent or buckled or broken by the ceaseless and powerful dance of the sea. These profoundly ingenious and beautifully complex dancing giants, the deep and stable semi-submersible, the ever-watchful and weather-vaning FPSO, the serene and deeply drafting spar, and the tautly tethered and immovable TLP, are a stunning and powerful testament to a new and deeply respectful engineering philosophy of compliance over resistance. They are the great enabling technologies that have allowed us to unlock the vast and previously unreachable resources of the truly deep ocean. But the success of this intricate and perpetual dance is entirely and completely dependent on one final and absolutely critical system. The great dancer must be at all times securely and unbreakably tethered to the dance floor. How then do you anchor a city-sized floating structure in a water depth of over 2 kilometers with a level of strength and of resilience that is great enough to hold it perfectly on station, with a precision of just a few meters, during the full, the unrestrained, and the almost unimaginable fury of a Category 5 hurricane? This leads us into the dark, the silent, and the immensely powerful world of the seabed, and to the colossal and almost unbelievably strong science of deep water mooring. The great floating giants of the deep ocean, for all their ingenious stability and their graceful compliance with the rhythm of the sea, are nothing without their connection to the earth. A floating platform that is not securely anchored is not a production facility. It is merely a ship, adrift on the currents. The entire philosophy of the dancer is therefore completely and utterly dependent on one final and almost unbelievably strong system, the mooring. This is the platform's invisible and unbreakable leash, a complex and highly engineered network of anchors, of chains, and of ropes that is the true unsung hero of all deep water engineering. It is not a simple case of dropping a heavy weight to the bottom. It is the science of creating a dynamic, a resilient, and an immensely powerful web that must hold a city-sized structure perfectly on station, with a precision of just a few meters, in a water depth of several kilometers, all while being subjected to the full, the unrestrained, and the almost unimaginable fury of a once-in-a-century hurricane. This great invisible web begins its life with a profound and powerful connection to the seabed itself. The anchor for a deep water platform is not the familiar shape of a nautical anchor. It is a colossal and highly specialized piece of geotechnical engineering. In the soft, muddy clays that are common in deep water environments, the preferred solution is the suction pile, or the suction caisson. This is a massive, hollow, and open-bottomed steel cylinder, which can be over 20 meters long and 8 meters in diameter. It is lowered to the seabed by a crane, and a powerful underwater remotely operated vehicle, or ROV, then latches onto a valve at the top of the pile. The ROV then begins to pump the water out from the inside of the sealed pile. This creates a massive pressure difference between the inside of the pile and the immense ambient hydrostatic pressure of the deep ocean outside. The ocean itself, with its thousands of tons of weight, then becomes a colossal hydraulic press, pushing the pile down with an immense and almost silent force, driving it deep into the seabed until it is a permanent and unshakable foundation point. For harder seabeds, a massive, high-capacity drag embedment anchor may be used, a colossal plow-like device that is designed to dig itself ever deeper into the ground the harder it is pulled upon. Stretching from this immovable foundation on the seabed up through the immense dark water column is the mooring line itself. In the profound depths of the modern offshore field, a simple continuous steel chain is not a viable option. Over a distance of several kilometers, the sheer self-weight of the chain would be so immense that it would be almost impossible to support. The modern deep-water mooring line is therefore a sophisticated and carefully engineered composite structure. The section at the very bottom, connected to the anchor, is indeed made of a heavy, large-diameter steel chain. This bottom chain is designed to be incredibly tough, to resist the constant abrasion as it moves across the seabed, and its immense weight plays a crucial role in the physics of the system. The long middle section of the line, which can be several kilometers in length, is then made from a modern miracle of material science, a thick, braided, and neutrally buoyant rope made of high-strength polyester. These synthetic ropes are a marvel of technology, a material that is, pound for pound, stronger than steel, but which is almost weightless in the water. And finally, the top section of the line, which connects to the platform, is once again made of a heavy, durable steel chain designed to withstand the wear and tear of the wave zone and the connection to the platform's hardware. The true genius of this composite system lies in the elegant and fundamental physics of the catenary curve. The mooring lines are not pulled taut between the platform and the anchor. They are deliberately installed with a great deal of slack, so that they hang in a long, gentle, and sweeping curve through the water. It is the shape of a simple chain hanging under its own weight. When the platform is sitting in its central calm weather position, a significant portion of the heavy bottom chain of each mooring line is lying dormant on the seabed. When a great wave or a powerful gust of wind pushes the platform off its station, it begins to pull on the mooring lines. But the platform does not feel the immediate, jarring shock of a taut line. Instead, the first thing it must do is to slowly and progressively lift the immense weight of that dormant bottom chain off of the ocean floor. This very act of lifting the heavy chain is what provides the restoring force. It acts as a massive, powerful, and yet incredibly soft natural spring. The further the platform moves, the more heavy chain it has to lift, and the greater the gentle but firm pulling force that will guide it back to its center. While the catenary mooring is the classic and most common solution, a different philosophy is sometimes required, particularly for platforms, like the tension leg platform, that need to restrict their horizontal movement. This is the taut leg mooring system. This method takes advantage of the incredible lightweight strength of the modern synthetic polyester rope. In this system, the mooring lines are connected, in a much more direct and almost straight line between the anchor on the seabed and the platform above. The restoring force in this system does not come from the lifting of a heavy chain, but from the inherent and predictable elasticity of the polyester rope itself. The ropes are installed under a high degree of tension, and as the platform is pushed by the wind and the waves, these immensely strong synthetic ropes stretch like giant underwater bungee cords. This stretching action absorbs the energy of the ocean and provides the powerful restoring force that keeps the platform on station. It is a stiffer and more responsive system than the catenary, and it allows for a much smaller and more controlled operational footprint on the seabed. The installation of these colossal and complex mooring systems in a water depth that can be as great as 3 kilometers is one of the most challenging and dangerous operations in all of marine construction. This is the work of a specialized and incredibly powerful class of vessel, the Anchor Handling Tug Supply, or AHTS vessel. These ships are the powerful and almost legendary workhorses of the offshore world. The process is a ballet of immense power and microscopic precision. The AHTS will first load the multi-ton anchor and the several kilometers of meticulously arranged chain and rope onto the large open deck at its stern. It will then sail to the precise, predetermined GPS coordinate where the anchor is to be deployed. Then, in a highly complex and often dangerous operation, the entire mooring leg is carefully paid out over the stern of the vessel, and is lowered under perfect control through the immense water column to the seabed below. For a suction pile, the AHTS will work in concert with a subsea construction vessel that is operating the ROV that will perform the final critical pumping operation. This process is repeated, one leg at a time, for all of the 12 or 16 or even 20 mooring lines that may be required to secure a single platform. With the great invisible leashes now firmly and permanently anchored to the deep, silent, and unseen earth of the seabed, the final connection, the connection to the dancing platform itself, can be made. The top chains of the mooring lines are hoisted from the water and are threaded through a series of massive and incredibly strong steel openings in the platform's hull, known as fairleads. These fairleads are designed to be exceptionally smooth, to allow the chain to move with the platform's motion without being damaged. Once inside the platform's great hollow columns or on its main deck, the chains are connected to a series of colossal winches and chain stoppers. These immensely powerful hydraulic machines are then used to pull in the final sections of the mooring lines, applying a precise and carefully calculated amount of tension to each and every line in the system. This final act of tensioning is what centers the platform in its final operational position, and what ensures that the load from any future storm will be perfectly and evenly distributed throughout the entire, redundant, and immensely powerful mooring web. With its great and now fully tensioned, invisible leashes firmly and securely connecting it to the deep and silent earth of the abyssal plain, the great dancing giant is finally complete. The mooring system, a masterpiece of modern material science, of elegant applied physics, and of a profound and hard-won naval precision, now holds the colossal floating platform perfectly on station, ready to ride out and to survive, the worst and most violent that the ocean can throw at it for an entire generation. The great platform is now in place. It is now secure, and its flexible risers are now connected to the rich and valuable wellheads that lie on the ocean floor, far, far below. But a new and a final and a profoundly challenging question now presents itself. How do we create the last and the most vital link in this great deep water chain? How do we create the great, the continuous, and the permanent undersea arteries that will carry the precious resources from this incredibly remote deep water outpost across hundreds of kilometers of hostile, of unseen, and of unforgiving terrain, all the way back to the safety and the security of the shore? The great offshore platform, Whether it is a rigid, unyielding fortress of steel or a graceful dancing giant of the deep, is a marvel of standalone engineering, but in its magnificent isolation, it is utterly useless. It is a heart without an artery, a lung without a bronchial tube. For this entire, colossal, and multi-billion-dollar undertaking to have any purpose at all, a final, a vital, and an incredibly long link must be forged. A continuous, a secure, and a permanent pathway must be created to transport the precious, hard-won resources from this remote, deep-water outpost across hundreds of kilometers of hostile, of unseen, and of completely unforgiving submarine terrain, all the way back to the safety and the security of the shore. This is the world of the subsea pipeline, the quiet, the unseen, and the absolutely indispensable circulatory system of our entire global energy network. A subsea pipeline is not the simple, hollow tube of our imagination. It is a highly engineered and deceptively complex, multi-layered structure, a technological sandwich that is designed and fabricated to survive completely unaided for a multi-decade lifespan in one of the most corrosive and high-pressure environments on the planet. Its life begins as a section of high-strength carbon steel pipe, forged and welded with an almost perfect degree of integrity. This raw steel core is then given its first and most critical layer of armor, the corrosion coating. This is a thin but incredibly robust layer of a material known as fusion-bonded epoxy, which is applied at the factory under perfect cleanroom-like conditions to create a permanent and impermeable barrier against the relentless chemical attack of the salt water. On top of this, a second and far more massive layer is often applied, the concrete weight coating. This is a thick and very heavy layer of reinforced concrete that gives the pipeline the necessary negative buoyancy, the sheer dead weight that will keep it stable and firmly planted on the ocean floor. It also acts as a tough physical shield, protecting the precious steel pipe within from the immense dragging forces of a fishing trawler's nets or the accidental impact of a dropped object from the surface. To transform these thousands of individual, 12-meter long and multi-layered pipe sections into a single, continuous, and unbroken artery that can be hundreds of kilometers long requires a very special and a very powerful kind of machine. This is the pipelay vessel, a floating and often moving factory of immense scale and complexity. The most modern of these vessels are vast, city-sized ships, which are held in their precise, predetermined location on the surface of the ocean, not by anchors, but by a sophisticated and computer-controlled dynamic positioning or DP system. This is a network of powerful and fully articulating thrusters, which are constantly and automatically firing, making thousands of tiny adjustments every second to counteract the forces of the wind, the waves, and the currents. This allows these immense floating factories to maintain their position on the sea with a precision of less than a meter, and to move along a pre-programmed route with a slow, a steady, and an almost perfect control. The most common and the classic method of assembling and laying this continuous underwater artery is known as the S-lay method. On the long open deck of the pipe-lay barge, a horizontal factory-like assembly line, known as the firing line, is set up. The individual pipe joints are lifted onto this line and are moved through a series of specialized workstations. At the first stations, the ends of the pipes are beveled and then clamped together, and a team of highly skilled automated or manual welders will create a perfect full penetration weld, fusing the two sections into one. At the next station, this new weld is immediately and non-destructively tested, often using a robotic ultrasonic scanner that can detect even the most microscopic of flaws. At the final stations, the bare steel of the welded joint is coated with the same multi-layered corrosion and weight protection as the rest of the pipe, creating a completely seamless and uniformly protected tube. As the barge then moves slowly forward, this now continuous and ever-growing pipeline is paid out over the stern of the vessel, in a long and graceful curve down to the seabed. The shape that this pipe makes, with its long, gentle upper bend over the stern, and its long lower bend as it touches down on the seabed, forms a distinct and characteristic S shape, giving this highly efficient and rapid method its name. This classic S-lay method, however, begins to face challenges as the pipeline journey moves into the truly and profoundly deep waters of the world. In a water depth of several kilometers, the long horizontal section of the pipe that is suspended between the vessel and the seabed is subjected to immense and potentially damaging tension forces. For these deep water challenges, a different and more specialized technique is required, the J-lay method. In this philosophy, the entire factory-like assembly process is rotated from the horizontal to the vertical. The pipe-lay vessel is equipped with a massive and often tilting tower. The individual pipe joints are lifted into this tower, where they are welded together in a vertical or a near vertical orientation. The completed pipeline is then paid out directly downwards from the bottom of this tower and descends through the water column in an almost perfectly straight line. It has only one single gentle bend, just as it lands on the seabed, forming a distinct J shape. This method is slower and more complex than the S-lay, but by eliminating the long high-tension upper curve, it puts far less stress on the pipe, making it the preferred and the safest solution for the extreme and unforgiving challenges of the ultra-deep water environment. The pipeline is not always simply laid to rest on the surface of the seabed. In many cases, particularly in shallower coastal waters where it could be at risk from ship anchors or fishing activity, the pipeline must be buried. This is achieved through a process of post-lay trenching. After the pipeline has been laid on the seabed, a second and highly specialized subsea machine is brought to the site. This can be a massive underwater plow, which is towed along the seabed by a powerful vessel, lifting the pipeline, digging a trench beneath it, and then laying the pipeline back down into the new trench, all in a single continuous pass. An alternative method, particularly in softer soils, is to use a jet trenching remotely operated vehicle. This robotic underwater tractor will travel along the pipeline, and using a series of incredibly powerful high-pressure water jets, it will fluidize the soil directly beneath the pipe, allowing the heavy pipeline to sink under its own weight into the temporary liquid-like trench, which will then naturally backfill with the surrounding sediment. The final, and one of the most technologically challenging acts in the creation of this subsea artery, is the final connection. To connect the end of the long pipeline to a fixed structure, like a platform, or to a specific piece of subsea infrastructure, like a wellhead, requires a level of precision and of dexterity that is almost impossible to achieve from the surface. This is the work of the deep sea surgeon, the advanced and highly capable remotely operated vehicle, or ROV. These powerful robotic submarines, which are tethered to and controlled from a mothership on the surface, are the true hands and the eyes of the engineer in the deep. Guided by a skilled pilot and equipped with a suite of powerful lights, of high-definition cameras, and of incredibly strong and remarkably delicate hydraulic manipulator arms, an ROV can perform a range of complex subsea construction tasks, from turning valves to connecting hydraulic lines, and, most critically, to guiding the final flanged end of the pipeline into its receiving hub, and then tightening the immense hydraulic bolts that will form the final permanent and leak-proof seal. With the great, and now continuous subsea artery finally laid, now buried where necessary, and now securely and perfectly connected at both of its ends, the great offshore production field is, at long last, complete. A permanent, a secure, and an almost unbelievably long and complex path has now been created, a path that allows the hidden and precious resources of the deep ocean to be safely transported from the heart of a remote and hostile frontier, all the way back to the shores of our civilization. This entire, colossal, and almost symphonic undertaking, from the very first exploratory survey, to the fabrication of the platform, to the installation of the mooring, and to the final subsea connection, is a profound testament to an almost unparalleled level of coordination between a dozen different and highly specialized engineering disciplines. But what happens when the very ground that all of these incredible structures are built upon is not as stable or as silent as it seems? The deep ocean floor is not a static and unchanging place. It is a dynamic and a living environment, the site of immense and slow-motion submarine landslides, of powerful sediment-laden turbidity currents, and of other great geological hazards that can threaten to destroy even these immense and brilliantly engineered structures. How then do our engineers design for, and how do they protect their great offshore creations from the hidden and the often unpredictable dangers of a seabed that is itself alive and in constant and powerful motion? The great heroic structures of the offshore world, the fortresses of steel and the dancing giants of the deep, are all designed with a profound and an intimate understanding of the immense and violent forces of the ocean's surface. They are built to withstand the 100-year storm, the rogue wave, and the relentless driving currents. But the seabed, the very foundation upon which this entire colossal enterprise is built, is not the stable, the solid, and the unchanging bedrock of our imagination. The deep ocean floor is a dynamic, a living, and an often treacherous landscape in its own right. It is a world that is subject to its own unique and powerful geological hazards, to immense and slow-motion avalanches of mud, and to powerful, unseen underwater currents of sediment that can threaten to destroy or to bury even the most well-engineered of structures. The final and most subtle layer of offshore engineering is therefore the science of understanding, of predicting, and of designing for the hidden and often unpredictable dangers of a seabed that is itself alive and in constant and powerful motion. The first and the most colossal of these hidden dangers is the submarine landslide. The continental slope, the long, gentle gradient that connects the shallow waters of the shelf to the deep abyssal plain, is one of the largest and most dynamic geological features on our planet. For millions of years, the rivers of the world have been washing a ceaseless supply of fine-grained silts and clays into the ocean, and these sediments have slowly accumulated on this slope, creating a vast and often unstable layer of soft, waterlogged material that can be kilometers thick. Over time, these immense, oversteepened, and water-saturated slopes can be brought to a critical point of instability by a variety of triggers: the subtle but powerful ground shaking of a distant earthquake, the slow buildup of pressure from pockets of natural gas that are trapped within the sediments, or even the simple, relentless, and gravitational pull on the ever-growing mass of the sediment itself. When this failure point is reached, a vast section of the seabed, sometimes with a volume of many hundreds of cubic kilometers, can collapse and slide in a slow motion but utterly unstoppable avalanche down the continental slope and into the deep ocean. A direct consequence of these immense submarine landslides, and in some ways an even more destructive and far-reaching hazard, is the turbidity current. This is not a simple sliding mass of mud. It is a dense and often incredibly fast-moving underwater avalanche that is composed of a turbulent and chaotic mixture of water and suspended sediment. These currents, which can be triggered by a landslide or by a major sediment-laden river flooding directly into the sea, can behave like a dense, heavy fluid. and they will flow under the force of gravity down the continental slope, and can travel for many hundreds or even thousands of kilometers across the flat abyssal plains of the deep ocean, at speeds that can exceed 70 kilometers per hour. These powerful and almost invisible underwater events are one of the most destructive forces in the deep sea, a scouring, abrasive, and unstoppable river of mud and sand that can snap a thick steel subsea telecommunications cable, or a major oil pipeline as if it were a dry twig, and can bury entire sections of the seabed under many meters of new sediment in a matter of hours. To protect a multi-billion-dollar and decades-long offshore investment from these powerful and almost silent geological threats, the engineers must first become forensic geologists. They must meticulously map the danger. This is achieved through a specialized and highly detailed geohazard survey, using the high-resolution three-dimensional maps of the seabed that were created by the multi-beam echo sounder. The geophysicist will search for the telltale morphological signs of past landslides, the great curved amphitheater-like scars on the continental slope where a past slide was initiated, and the vast lumpy and chaotic debris fields on the abyssal plain where the material from that slide finally came to rest. They will then use the deep penetrating vision of the sub-bottom profiler to peer beneath the skin of the seabed, looking for the hidden weak layers of sediment, the buried pockets of shallow gas, and the ancient, unstable fault lines that could be the trigger for a future catastrophic failure. This is the painstaking detective work of finding the geological smoking guns, of identifying the areas where the seabed is and is not safe to build. Armed with this detailed and comprehensive map of the hidden geological dangers, the first, the most important, and the most effective engineering solution is, in a word, avoidance. The vast majority of the time, the safest and most economical way to deal with a major geohazard, such as a large and unstable submarine slope, is to simply not go there. The proposed route of a new subsea pipeline will be meticulously re-examined and replotted, a process of finding a new and delicate balance between the shortest and therefore most economical path and the safest and most geologically stable path. This can involve adding many dozens of kilometers to the total length of a pipeline, a decision that can add hundreds of millions of dollars to the cost of a project, but which is a necessary and a prudent investment to ensure the long-term 100-year survival of this critical and irreplaceable piece of infrastructure. The most brilliant engineering solution to a problem is often the intelligence and the humility to simply go around it. There are times, however, when a region of known or potential geological instability simply cannot be avoided. In these cases, the infrastructure must be armored, or a subsea pipeline that must cross a hazardous zone. A variety of brute force protective measures can be deployed. The most common of these is the practice of rock dumping. A specialized and dynamically positioned fall pipe vessel will sail to the location, and using a long, articulated pipe that extends down to the seabed, it will carefully and precisely place many thousands of tons of specifically graded rock over the top of the pipeline. This creates a large, heavy, and stable berm, a protective stone fortress that is designed to shield the pipeline from the impact of a small turbidity current, or to add enough weight and stability to the surrounding soil to prevent a small, localized landslide from occurring. In conjunction with this, the design of the pipeline itself can be strengthened with a thicker steel wall and the use of special high-strength and more ductile steel alloys that are better able to withstand the immense dragging forces of a slow-moving mudslide. For the vital and flexible arteries that connect a floating platform to the seabed, the risers, the protection against geohazards is achieved through a philosophy of resilience and of engineered compliance. The steel Kateri riser, or SCR, is a perfect example of this. Instead of a simple vertical pipe that would be snapped by any significant movement of the seabed, the SCR is a single continuous and immensely long steel pipe that hangs in a long, gentle, and sweeping Kateri curve between the floating platform and its touchdown point on the seabed. This great curved shape, which has a significant amount of slack, is inherently able to accommodate a large degree of movement. If a slow motion landslide or a gradual subsidence causes the touchdown point of the riser to move by several meters, the gentle catenary curve will simply adjust, absorbing the movement without putting an unsustainable level of stress on the pipe itself. This, combined with the use of highly engineered tapered stress joints at the touchdown point, provides a robust and a resilient solution that allows this most vital of connections to survive in a world where the very ground beneath it is in motion. By meticulously and painstakingly mapping the faint, ghostly scars of ancient and long-dead underwater landslides, by charting the likely paths of the invisible and powerful submarine avalanches, and by then choosing a prudent and a carefully considered path of either cautious avoidance or of brute force structural armoring, the offshore engineers can finally create a structure that is safe not only from the loud and the violent and the chaotic forces of the water above, but also from the slow, the silent, and the often hidden violence of the earth below. The great offshore system, from its deepest foundation to its highest deck, is now at last secure in its place. But all of these immense and magnificent structures, the great fortresses of steel and of concrete, and the graceful deep-water dancers, are all built for a single, an ultimate, and a profound purpose: to extract the precious and the powerful resources that are trapped in the deep earth beneath them. This requires one final and one truly incredible act of high technology engineering. It requires us to drill. How then do we drill a hole that is often many thousands of meters deep into the hard and unforgiving rock of the earth's crust, all from the deck of a constantly moving platform, through a kilometer or more of open and often violent water, in one of the most challenging, the most dangerous, and the most immensely high-pressure environments that has ever been conquered by man, with the great offshore structure, now a permanent and secure feature of the marine landscape, whether it is a rigid fortress pinned to the seabed or a graceful dancer held in place by its unbreakable leashes. The final and ultimate purpose of this entire colossal undertaking can at long last begin. The platform is not the prize, it is merely the key, the true treasure. The vast and powerful reserves of energy that have been the object of this entire multi-billion-dollar quest lies trapped many thousands of meters deeper still, locked away in high-pressure geological formations deep within the Earth's crust. The final act of this great endeavor is to create a connection to this deep world, to drill a long, a slender, and a perfectly controlled pathway from the deck of the platform down through the immense dark water column, and then for many kilometers more into the hard and unforgiving rock below. This is the world of offshore drilling, a discipline that combines the brute force of mining with the delicate precision of remote surgery, and which is, without question, one of the most challenging, the most dangerous, and the most technically sophisticated forms of engineering ever conceived by man. For the initial exploratory phase of this work, the primary tool is often a highly advanced and specialized vessel known as a drill ship. This is a massive self-propelled ship, often as long as 2 football fields, that is in its essence a complete and mobile deep-water drilling rig. At the center of its hull, a feature that makes it instantly recognizable is the moon pool. This is a large square opening that passes directly and vertically through the entire vessel, from the drill floor on the main deck down to the open sea below. This seemingly simple hole is a critical piece of engineering. It creates a small and relatively sheltered patch of water at the very center of the vessel's footprint, a calm oasis that is protected from the violent slapping action of the waves against the hull. It is through this moon pool that the entire multi-thousand-ton apparatus of the drilling system, the drill string, the riser, and the blowout preventer, can be safely and vertically lowered into the deep ocean, a protected gateway that serves as the first critical link between the industrial world on the deck and the dark natural world far below. The greatest initial challenge of drilling from a floating vessel is to create a secure and a continuous connection between the constantly moving ship on the surface and the fixed, stationary wellhead that is to be established on the seabed, which can be 2 or 3 kilometers beneath it. This is the job of the marine riser. The riser is a colossal and slightly flexible large diameter pipe that is assembled section by section and is lowered from the drill ship to latch onto the wellhead. This great vertical umbilical serves two absolutely vital and simultaneous purposes. Firstly, it acts as a physical guide, a conduit through which the smaller rotating drill string can travel on its long journey down to the well. And secondly, and more critically, it provides a closed, contained pathway for the drilling fluids or mud to be circulated from the ship down the drill string and then back up to the surface in the space between the drill string and the riser, a closed loop that prevents these fluids from being spilled into the marine environment. The entire multi-thousand-ton weight of this riser is supported by a series of powerful hydraulic tensioning systems on the drill ship, which are constantly and automatically adjusting, stroking in and out to perfectly compensate for the vertical, heaving motion of the ship in the waves, keeping the riser under a constant and a perfect tension. The single greatest and most ever-present danger in all of oil and gas drilling is the risk of an uncontrolled and potentially catastrophic release of the high-pressure hydrocarbons from the deep reservoir, an event that is known as a blowout. To guard against this, the most critical, the most robust, and the most complex single piece of equipment in the entire operation is installed at the very mouth of the well, on the seabed. This is the blowout preventer, or the BOP stack. It is a colossal and multi-story high assembly of massive and highly redundant hydraulic valves, each one designed to be a fail-safe barrier against the immense upward rushing pressure of the well. The BOP stack is a fortress of valves, containing a series of different and increasingly powerful sealing mechanisms. These include the annular preventers, which are large steel-reinforced, rubber donut-like seals that can be hydraulically squeezed to close and to seal around the drill pipe. Below these are a series of pipe rams, which are two opposing steel blocks that can be powerfully driven inwards to achieve a similar seal. And at the very bottom, the final and the most absolute line of defense are the blind shear rams. These are two massive and opposing blades of hardened steel, which in a catastrophic last resort emergency can be activated to slide across and to physically slice the thick, high-strength steel drill pipe in two, and then to seal the well completely shut. With the great redundant guardian of the well now in place, the true process of drilling can begin. The drill string is a long and incredibly strong strand of interconnected 10-meter-long sections of high-grade steel pipe. At the very bottom of this string, thousands of meters below the platform, is the drill bit, a marvel of modern material science. It is a complex and brutal tool, often with a series of rotating conical cutters, or a series of fixed industrial diamond or tungsten carbide cutters, which are designed to pulverize and to grind their way through the hardest and most abrasive of rock formations. The real and unsung hero of this process, however, is the drilling mud. This is a complex and carefully engineered synthetic fluid that is constantly pumped at high pressure from the surface, down through the center of the hollow drill string. This mud serves many purposes. It cools and it lubricates the spinning drill bit. and it carries the crushed rock cuttings back up to the surface. But its most critical function is to provide the primary well control. The density, or the weight, of this column of mud is carefully controlled to exert a precise amount of hydrostatic pressure at the bottom of the hole, a pressure that is deliberately designed to be slightly greater than the pressure of the oil and the gas in the deep reservoir, and which acts as the first and the most important barrier that keeps those powerful hydrocarbons safely in their place. The great hydrocarbon-rich reservoirs that are the target of this entire operation are not always located directly beneath the platform. They are often complex, folded, and geographically dispersed formations. The modern well, therefore, is rarely a simple vertical hole. It is a complex and often multi-kilometer long, three-dimensional trajectory, a process that is known as directional drilling. To achieve this, a specialized piece of equipment known as a downhole motor or a rotary steerable system is placed at the bottom of the drill string, just above the drill bit. This allows the bit to be steered, to be pointed in a slightly different direction from the main axis of the well. This steering is guided by a sophisticated and incredibly robust suite of electronic sensors, a system known as measurement while drilling, or MWD, which is located just behind the motor. This system constantly measures the precise inclination and the azimuth of the wellbore, and it transmits this data in real time back to the driller on the platform, often using a series of encoded pressure pulses in the drilling mud itself. This allows the driller, sitting in a control room, thousands of meters above, to actively, and with a stunning precision, steer the drill bit through the deep earth, to hit a target that can be the size of a small room, but which is located many kilometers away from the platform. An open, raw, and unlined hole that has been drilled through thousands of meters of complex and often unstable geological formations cannot be left unsupported. The well must be made permanent and secure, a process that is achieved through a cyclical and a multi-stage process of casing and of cementing. The drilling of the well proceeds in a series of discrete sections. After a section of the hole has been drilled to its target depth, the entire multi-kilometer long drill string is pulled out of the hole. Then, a new string of a slightly smaller diameter, and this time made of large, heavy, and permanent steel pipe, known as casing, is lowered into the open hole. Once the casing is in place, the final critical step of cementing is performed. A specially formulated and often quick-setting cement slurry is pumped at high pressure down the inside of this new casing. It flows out of the bottom and then is forced back up into the small empty space, the annulus, between the outside of the steel casing and the raw open rock of the borehole. This cement is allowed to harden, and it creates a permanent and impermeable and a vital structural seal, which isolates the well from the surrounding rock formations, and which provides a solid and a secure foundation for the next and the deeper section of the well to be drilled. This process is repeated with a series of progressively smaller and smaller diameter sections of casing until the well has reached its final and its target depth. With the great, the deep, and the now perfectly secure well finally drilled, cased, and safely connected to the great production platform on the surface, the colossal, the complex, and the almost unbelievably expensive task of finding and of harnessing the great energy resources of the deep can, at long last, begin. The engineering of modern offshore drilling is a profound and a deeply humbling testament to our species' ability to operate with an almost unbelievable combination of brute geological power and of delicate and remote-controlled surgical precision in one of the most distant, the most dangerous, and the most challenging industrial environments that has ever been conquered. But this entire, vast, and incredibly sophisticated infrastructure of great deep water platforms, of immensely long pipelines, and of incredibly complex and deep wells, has all been designed to serve a world and to feed an economy that is now in a state of profound and of irreversible transition. As our global civilization begins its long and historic pivot away from its reliance on fossil fuels, a new, an even grander, and a perhaps even more challenging engineering frontier is now rising on the horizon. How then do we adapt the immense, the hard-won, and the powerful skills and technologies of the great offshore industry to find, to harness, and to deliver a new, a cleaner, and a far more sustainable form of energy from the deep? This leads us, inevitably, to the great, the modern, and the wind-swept frontier of all offshore engineering, the world of the great offshore wind farm. The vast and powerful infrastructure that we have so far explored, the great fortresses of steel and the deep-water dancers of the abyss, were all conceived and constructed to serve the defining energy source of the 20th century. But as our global civilization begins its long, its difficult, and its absolutely essential pivot towards a new and more sustainable future, the immense, hard-won, and powerful skills of the offshore engineer are being adapted and repurposed for a new and an even grander challenge. The new frontier is not about drilling down into the deep earth, but about reaching up into the sky. It is the quest to harvest a different, a cleaner, and an even more powerful resource from the sea, the immense and ceaseless energy of the wind. The great modern offshore wind farm is the new chapter in our long story of building in the ocean, a chapter that is not about extraction, but about a silent, a clean, and a perpetual harvest. The reason that we are willing to undertake the immense expense and the profound engineering challenge of building these great power plants in the middle of the sea is simple. The wind over the open ocean is a fundamentally different and far more powerful resource than the wind on land. Unimpeded by the friction of hills, of forests, and of buildings, the ocean winds are on average significantly stronger and far more consistent than their terrestrial counterparts. This is a fact of profound importance, because the amount of power that a wind turbine can generate is not linearly related to the wind speed. It is exponentially related to it, to the power of 3. This means that a small increase in the average wind speed results in a massive and almost disproportionate increase in the amount of clean energy that can be produced. The offshore wind farm, therefore, represents a journey to the very heart of the world's most powerful and most reliable wind resources, a place where we can build taller, more powerful, and more efficient machines than we ever could on land. For the great shallow water wind farms that make up the vast majority of the world's current offshore capacity, the foundational workhorse of the industry is a structure of elegant and brutalist simplicity, the monopile. This is, as its name suggests, a single colossal hollow steel pile, a structure that can be over 100 meters long, more than 10 meters in diameter, and can have a steel wall thickness of over 10 centimeters. It is a structure of almost unimaginable strength and stiffness. These colossal tubes are fabricated on land, and are then transported, one by one, out to the site by a specialized installation vessel. Here, a massive and incredibly powerful hydraulic hammer, the same technology we have seen used to pin the great jacket platforms to the seabed, is used to drive this single colossal pile deep into the seabed, a process that can take many hours of relentless, thunderous blows. Once the monopile is driven to its target depth, a second crucial component, the transition piece, is lowered over its top. This is a large and often brightly painted steel cylinder that is grouted into place, and which provides a perfect and absolutely level flanged connection, the platform upon which the great white tower of the wind turbine itself will be built. As the wind farm industry, in its relentless quest for ever stronger and more consistent winds, begins to move into deeper and deeper waters, A point is reached where the single massive monopile becomes too long, too flexible, and too difficult to install. For these deeper water challenges, the industry has turned to a familiar and a trusted technology, borrowed directly from its older cousins in the oil and gas sector, the jacket foundation. These are the very same open lattice steel truss structures that we have seen before, but they have been optimized, they have been lightened, and they have been re-engineered for their new purpose. Instead of a single massive and centralized structure, the wind farm jacket is a much smaller, a much lighter, and a mass-produced item, designed with 3 or 4 slender legs, which are then pinned to the seabed with smaller, more conventional piles. The great hard-won knowledge of how to design, how to fabricate, and how to install these immensely strong and hydrodynamically efficient structures, a knowledge that was perfected over 50 years of offshore oil and gas exploration, is now being directly and brilliantly applied to the challenges of this new and sustainable energy frontier. The installation of the wind turbine itself, a delicate and a precision-engineered machine that is over 200 meters tall, in the choppy and unpredictable environment of the open sea, requires a unique and a highly specialized type of vessel. This is the Wind Turbine Installation Vessel, or the WTIV. The most advanced of these are massive self-propelled jack-up vessels. These ships will sail to the offshore construction site, carrying all of the components of a complete wind turbine, the 3 or 4 massive steel tower sections, the colossal and incredibly heavy generator housing known as the nacelle, and the 3 huge and gracefully aerodynamic blades on their large open decks. Upon arriving at the pre-installed foundation, the vessel deploys a series of 4 massive lattice-like legs down to the seabed. It then engages a powerful hydraulic jacking system, and it lifts its entire multi-thousand-ton hull completely up and out of the water, transforming itself from a floating ship into a fixed and absolutely stable offshore platform. From this profoundly stable, man-made island, the vessel's own immense and onboard crane can then begin the slow, the delicate, and the precise work of lifting and of assembling the multi-hundred-ton components of the wind turbine, a task that would be completely impossible to perform safely from a moving, floating vessel. A great offshore wind farm is not just a collection of individual turbines. It is a single, unified, and interconnected power plant, and to function as such, it requires its own vast and completely unseen nervous system. This is the inter-array cable network. This is a complex and often redundant subsea web of medium voltage armored power cables that connects the base of each and every wind turbine to its neighbors, and then directs the collected flow of energy towards a central point. These vital and surprisingly delicate arteries are laid by another specialized class of vessel, the cable lay vessel. As the cable is paid out, it is often simultaneously buried in the seabed for its protection. This is achieved by a subsea cable plow, a large remotely operated machine that is towed along the seabed, which lifts the cable, digs a trench beneath it, and then lays the cable down into the new trench, all in a single, continuous, and surprisingly gentle operation. All of the power that is generated and collected by this vast and sprawling web of hundreds of individual turbines must then be gathered. It must be conditioned, and it must be prepared for its long and final journey to the shore. This is the job of the offshore substation. This is the true and the single beating heart of the entire wind farm. It is a massive and often multi-story electrical substation, complete with colossal transformers, with high-voltage switchgear, and with crew facilities, all of which is housed in a large topside module that is placed on its own dedicated and centrally located foundation in the middle of the sea. The offshore substation is the Great Collection Point, the place where all of the individual medium voltage streams of power from the inter-array cables are brought together, where the voltage is dramatically stepped up to a much higher and more efficient transmission level, and where the power is stabilized and prepared for its final and most important journey. The final and the longest artery in this great offshore power generation system is the export cable. This is the main, the single, and the absolutely critical high voltage power cable that carries the entire combined and now fully conditioned electrical output of the whole wind farm back to the land. These are some of the most complex and most expensive cables on Earth, a marvel of material science, with a core of massive copper or aluminum conductors surrounded by multiple concentric layers of insulation, of armoring, and of waterproofing. The laying of these immense and surprisingly fragile cables, often over a distance of more than 100 kilometers, is a slow, a painstaking, and a highly specialized operation. A final and a vital act of connection that allows the silent, the clean, and the powerful harvest of the great and ceaseless ocean winds to finally come ashore and to power our world. The great, the silent, and the gracefully turning offshore wind farm, a vast and a sprawling and a subsea city of hundreds of towering white giants, is the new and the hopeful frontier in our long, our complex, and our often fraught relationship with the great and powerful ocean. It is a profound and a moving testament to our species' ability to adapt the immense, the powerful, and the hard-won knowledge of a fading and a carbon-intensive industrial age to the new, the urgent, and the life-sustaining needs of a new and a far more sustainable one. We have now explored the great fortresses, the graceful dancers, the deep and silent arteries, and the great, clean power plants of the offshore world. But all of these immense and magnificent structures, whether they are built for oil or whether they are built for wind, must ultimately, and in some way return to or pass by the land. What happens then? At this critical, this powerful, and this often violent and unforgiving interface between the great fluid energy of the sea and the solid and the immovable permanence of the shore. How do we build the great ports, the colossal breakwaters, and the vital coastal defenses that protect our civilization from the ocean's most direct, its most relentless, and its most powerful attacks? The great engineering works of the deep ocean, for all their immense and complex challenges, are in many ways protected by the very depths in which they reside. They are shielded from the most violent and chaotic energies of the sea, which are almost all concentrated at the surface. But as our journey now takes us back towards the land, we arrive at the final and most ferocious of all marine environments. This is the coastline, the violent and unforgiving margin between the sea and the shore. This narrow and ever-shifting zone is the place where the full, the accumulated, and the untamed energy of the open ocean, an energy that has often traveled for thousands of kilometers across the globe, is finally and completely unleashed in a torrent of unimaginable power. To build here, to create the great calm harbors that are the indispensable gateways of our global economy, and to protect our coastal cities from the relentless attacks of the sea, requires a form of engineering that is, in its essence, a perpetual and a high-stakes defensive war. To understand the nature of this war, one must first understand the true nature of the enemy. An ocean wave is not a moving wall of water. It is a pulse of pure and often beautiful energy that is passing through the water. In the deep ocean, the individual particles of water are not traveling with the wave. They are simply moving in a small circular or orbital path. But as this pulse of energy moves out of the deep ocean and begins to approach the shallow waters of the coast, a profound and a violent transformation occurs. The bottom of the wave begins to feel the rising seabed, and this friction causes it to slow down. As the wave slows, its length decreases, and the immense energy that it is carrying has nowhere to go but up. The height of the wave begins to grow, dramatically and unstably, a process known as wave shoaling. It is this process that transforms a gentle, rolling, open ocean swell into a towering, steep, and angry monster, which then, at a critical point, breaks, releasing its entire accumulated and now highly concentrated payload of energy in a single catastrophic and immensely destructive explosion of white water and foam. The first, the oldest, and the most common of all human defenses against this colossal and repetitive assault is the rubble mound breakwater. This is not a simple and unthinking pile of rocks. It is a highly engineered and surprisingly sophisticated artificial mountain, a man-made reef that is designed with the specific purpose of forcing the great waves to break and to dissipate their energy before they can reach the harbor or the coastline that it is designed to protect. A modern rubble mound breakwater is a complex and carefully layered structure. Its great bulky interior, the core, is often made from smaller and cheaper quarry-run rock, its primary purpose being to provide the immense gravitational mass of the structure. This core is then protected by one or two progressively larger underlayers of more carefully placed stone. And finally, the entire structure is armored with its most critical and most expensive component, the great outer armor layer. This is a skin of immense and often interlocking natural armor stones, each of which can weigh over 40 tons, and which are designed to absorb and to break the full raw and unbridled power of the breaking waves. As the wave forces that must be conquered become ever larger, a point is eventually reached where even the largest and the heaviest of natural quarried stones are not sufficient. They can be picked up by the most violent of storm waves and tossed aside like pebbles. For these most extreme of environments, the engineer must create a new and even more powerful form of artificial armor. This is the world of the concrete armor unit. These are massive and highly complex, interlocking and precisely shaped concrete blocks that are designed to perform far more intelligently than a simple, heavy stone. The most famous and the most widely used of these is the dolos. This is a colossal and strangely beautiful concrete object shaped like an H anchor with an extra perpendicular fluke. This intricate and highly engineered geometry is designed not just to resist the waves with its own immense weight, but to actively and powerfully interlock with its neighbors. When a great wave strikes a dolos wall, the complex shapes of the units cause them to wedge and to tighten against one another, forming a single, unified, and incredibly strong yet also flexible and porous artificial shoreline. A concrete labyrinth that is designed to absorb and to dissipate the wave's energy with a brutal and an almost perfect efficiency. The construction of these great, man-made mountains of stone and of concrete is a slow, a methodical, and a highly skilled operation. It is a colossal and three-dimensional interlocking puzzle, and it must be assembled in one of the most violent and unforgiving of all construction environments. The immense multi-ton armor stones, or the 40-ton, and surprisingly fragile concrete dolos, must be placed with a very high degree of precision to ensure that they interlock correctly and form a stable and a powerful defense. This work is performed by a fleet of specialized and powerful marine construction equipment. From the sea, a massive, floating derrick crane, mounted on a large stable barge, will lift the great armor units and will lower them into position, its movements guided by a sophisticated, real-time differential GPS system. From the land, a massive, long-reach hydraulic excavator with its own GPS-guided bucket will meticulously pick and place each individual stone, its operator working with the skill and the delicate touch of a master stonemason, but with a pallet of 40-ton blocks. An entirely different philosophy for coastal defense is that of the vertical wall, an approach that is less common for exposed open ocean breakwaters, but which is the standard method for constructing the great quays, the wharves, and the piers that form the protected and operational heart of a modern port. This is the world of the caisson breakwater. In this method, a series of immense and hollow and box-like concrete structures, the caissons, are constructed in the calm and controlled environment of a dry dock on the shore. These colossal boxes, each of which can be the size of a large, multi-story building, are then sealed. They are floated out to the construction site, and they are then sunk with immense precision onto a pre-prepared and perfectly level gravel bed on the seabed. Once in place, these hollow boxes are then completely filled with sand or with rock, transforming them into a massive, a solid, and a completely immovable gravity wall. Unlike the sloping and porous rubble mound breakwater, which is designed to dissipate the wave's energy, the sheer, vertical face of a caisson breakwater is designed to reflect the wave's energy, creating a much calmer and more protected harbor environment behind it. The modern and more enlightened understanding of our coastal environments, however, is now leading to a profound and a necessary shift away from these great, hard, and often environmentally destructive engineering solutions. A new and a more sustainable philosophy of coastal defense is now emerging, a philosophy that is based on the principle of working with the immense power of nature rather than simply trying to build a bigger and a stronger wall against it. This is the world of soft coastal engineering and of the living shoreline. This approach seeks to protect our coast by restoring and by augmenting the natural and the incredibly effective defensive systems of the coastal environment itself. This can involve the practice of beach nourishment, where millions of cubic meters of new sand are dredged from offshore and are placed on an eroding beach, widening it and creating a massive and a natural and a sacrificial buffer that can absorb the energy of a storm. It can also involve the large-scale and ecologically powerful restoration of our natural coastal wetlands, of our salt marshes, and of our mangrove forests, all of which are nature's own perfect and self-repairing breakwaters. By building these immense and powerful and carefully engineered artificial reefs of great, interlocking stone and of colossal and precisely shaped concrete, and increasingly, by learning to work in a more intelligent and a more sustainable concert with nature's own softer and more resilient defenses, we have over the centuries learned how to tame the immense and the otherwise untamable and violent energy of the shoreline. We have used this hard-won knowledge to create the great, the calm, and the protected deep water harbors that are the single most vital and most indispensable gateways for our entire interconnected and globalized world. The engineering of the coast is, and it will always be, a perpetual, a high stakes, and an ever-evolving negotiation between the great and ever-growing ambitions of man and the timeless, the patient, and the immensely powerful forces of the sea. We have now explored the great fortresses of the deep, the silent arteries of the abyss, and the powerful, armored defenses of the coast. But our story, so far, has focused almost entirely on the immense scale and the impersonal, inhuman nature of these great projects. What then of the human scale? What is it actually like to live and to work for weeks and for months at a time in the remote, the dangerous, the isolated, and the completely alien offshore world? This leads us inevitably to the final chapters of our long journey, and to the remarkable and the rarely told story of the men and the women who call these great steel islands their home. We have now explored In immense and in intricate detail, the great machines, the colossal structures, and the brilliant and often counterintuitive engineering principles that allow us to build in the hostile and unforgiving world of the open ocean. But this entire vast and complex technological ecosystem, for all of its automated systems and all of its remote controlled robotics, is, in the final analysis, utterly and completely dependent on a final and an even more complex component, the human machine. The great steel islands that are scattered across the oceans of our world are not unmanned fortresses. They are populated, they are managed, and they are maintained 24 hours a day by a dedicated, and a highly skilled community of men and women. This is the story of the human scale, of the unique, the challenging, and the rarely seen world of the offshore worker, the final and most essential gear in the entire great deep water enterprise. The life of an offshore worker begins with a journey that is, in itself, a testament to the remote and isolated nature of their world. The primary taxi service to these steel islands is the offshore helicopter. The journey is a highly ritualized and safety-focused affair. Before even boarding, every passenger must don a heavy and cumbersome survival suit, a piece of equipment that is designed to protect them from the instant and lethal shock of the cold ocean water in the event of an emergency. The flight itself is a journey into a world of profound and beautiful emptiness. A 1 or 2 hour flight over a vast and often featureless and heaving gray sea towards a destination that is, for much of the journey, a single and almost invisible speck on a distant and an empty horizon. The alternative and the lifeline for all heavy equipment and supplies is the platform supply vessel, the great and powerful workhorse truck of the sea, which makes its slow and steady and vital journey to and from the platform, carrying the food, the water, the spare parts, and the thousands of tons of drilling mud and chemicals that are the essential and life-sustaining consumables of the offshore world. Upon arrival, the offshore platform reveals itself to be a self-contained, and an intensely structured vertical village. The living quarters, or the LQ, is a multi-story and often surprisingly comfortable module that is designed to be a safe haven from the noisy, the industrial, and the dangerous work that is happening just a few meters away. Life here is a world of compact and shared 2 or 4 person cabins, of a communal and 24-hour-a-day mess hall that must cater to the different sleep and work cycles of the day and the night shifts, and of a small and limited set of recreational facilities, such as a small gymnasium, a movie room, or a quiet lounge. It is a microcosm of a larger society, a small and incredibly diverse community of people from all over the world who must live and work together in close quarters in a state of almost complete and total isolation from their families and from the rest of the world, for many weeks or even months at a time. The rhythm of life on this steel island is dictated by the relentless and unforgiving demands of the work itself. The standard offshore work pattern is a long and a continuous rotation. A worker will spend 2 or 3, or in some cases 4 full weeks, living and working on the platform, followed by an equal and a much anticipated amount of time back on the shore. The working day is a long and a demanding 12-hour shift, after which the worker will hand over their duties to their back-to-back, the person on the opposite shift who performs the same role. The work itself is often a physically and a mentally demanding affair. It is a life lived on an open steel deck, exposed to the brutal and the often unpredictable weather of the open ocean, from the searing heat of the tropical sun to the freezing spray and the gale-force winds of a North Sea winter. It is a world of constant industrial noise, of the roar of the generators, the whine of the pumps, and the thunderous percussive clang of the work on the drill floor. It is an environment that demands a unique and a profound level of focus, of professionalism, and of personal resilience. This intense and inherently dangerous working environment has, over the decades, bred a deep, a powerful, and an almost religious devotion to the culture of safety. In the offshore world, safety is not a department or a set of rules in a manual. It is the fundamental and the non-negotiable organizing principle of every single action, of every single day. The day begins with a safety meeting, where the risks of every planned task are discussed and are mitigated. No single piece of work, not even the changing of a light bulb, can be performed without a formal and signed permit to work. The constant and the correct use of personal protective equipment, from the hard hat and the steel-toed boots to the safety glasses and the impact gloves, is a matter of absolute and unwavering enforcement. And most importantly, every single person on the platform, from the most junior of trainees to the most senior of managers, is given stop work authority, the absolute power and the profound personal obligation to immediately halt any operation at any time that they believe to be unsafe without any fear of repercussion, to prepare for a world where the unthinkable can and sometimes does happen. Every single person who sets foot on an offshore platform must first undergo a series of incredibly rigorous and often terrifying safety and survival training courses. The most famous and the most feared of these is the Helicopter Underwater Escape Training, or HUET. In this course, the trainees are strapped into a realistic and simulated helicopter fuselage, which is then lowered into a large, deep swimming pool. The simulator is then violently and without warning flipped upside down, and the trainees must, in the dark and the disorienting and the terrifying environment of the submerged and inverted cabin, remain calm and follow their procedures to successfully escape. In other courses, they are trained in advanced industrial firefighting, in smoke-filled and heat-intensive simulators, and they are trained in sea survival, where they must learn how to correctly deploy and how to survive in a life raft in a pool that is generating a simulation of a cold and a stormy sea. In the event that a worker becomes seriously ill or is injured, they are hundreds or even thousands of kilometers away from the nearest hospital. Every offshore platform is therefore equipped with its own, small, but highly advanced medical clinic, which is run 24 hours a day by a dedicated and highly trained offshore medic. But for the most serious of cases, a new and a powerful technology has become the vital lifeline to the shore: telemedicine. The offshore medic can use a secure and a high bandwidth satellite video link to connect in real time with a team of specialist emergency room doctors who are on call at a major hospital on land. Through this live video connection, the onshore doctor can see the patient, they can monitor their vital signs, and they can guide the offshore medic, step by step, through a series of complex and often life-saving medical procedures. A powerful and a long-distance collaboration that brings the expertise of a world-class hospital to the most remote and isolated of all industrial environments. This intense, this unique, and this highly structured human ecosystem, with its strange and unnatural rhythms, with its profound and its almost monastic isolation, and with its absolute and its all-encompassing devotion to the principles of safety and of survival, is the true, the living, and the beating heart that allows the great, the silent, and the unthinking steel islands of the ocean to function. It is a world of almost unimaginable physical and mental challenge, but it is also a world of profound and of deep and of lifelong camaraderie and of an unwavering and a mutual professional respect. We have now explored the full and the immense breadth of this offshore world, from the deepest and the most unseen of its foundations, to the high and the windswept and the intensely human lives of the people who call this strange and alien environment their home. But the incredible technologies that we have so far discussed are for the most part the hard-won and the well-established solutions that have been developed over more than a half-century of building in the sea. What then of tomorrow? As our insatiable and ever-growing reach continues to extend into ever more challenging and ever more extreme frontiers, into the crushing and the almost unbelievable pressures of ultra-deep water, and into the frozen, the grinding, and the ice-laden waters of the great and desolate Arctic. What new, and what even more audacious, and what revolutionary engineering solutions are now being developed to conquer these final and these most extreme of all the oceanic environments? Our long journey across the vast and complex world of offshore engineering has now brought us to the very edge of the map, to the final and the most challenging frontiers that remain to be conquered. The hard-won technologies and the profound knowledge that were gained on the continental shelves and in the deep waters of the world are now being pushed to their absolute limits. The relentless quest for resources and for energy is now taking us into two new and almost impossibly difficult environments. The first is the crushing and almost unbelievable pressure of ultra-deep water. The second is the frozen, the grinding, and the ice-laden darkness of the great and desolate Arctic. To build here requires a new generation of even more audacious and even more revolutionary engineering solutions. We must first travel down far beyond the familiar depths into the realm of ultra-deep water. We are now speaking of water depths that are greater than 2 or even 3,000 meters. Here, the hydrostatic pressures are so immense they can exceed 300 atmospheres, a force that can find and exploit the most microscopic of flaws in any material. In this profoundly remote and high-pressure world, the very idea of a surface platform becomes a secondary concern. The new philosophy is to move as much of the complex processing equipment as possible from the floating platform on the surface down to the cold, the dark, and the surprisingly calm environment of the seabed itself. This is the dawn of the subsea factory. These are not simple wellheads. They are complete and incredibly complex robotic processing plants with powerful multi-phase pumps to boost the pressure of the oil and gas, and with large separation units that can separate the oil, the gas, and the water at the source. All of this is designed to operate completely autonomously for decades in the crushing darkness with no possibility of human intervention. To install and to maintain these deep water factories requires a new generation of robotic workers. The tethered and human-piloted remotely operated vehicle, or ROV, is now being supplemented by the autonomous underwater vehicle, or AUV. These are intelligent and untethered robotic submarines that can patrol the deep, using advanced sonar and laser scanning to create perfect three-dimensional maps of the subsea infrastructure, and using artificial intelligence to detect any potential flaws or failures before they become catastrophic. From the crushing darkness of the deep, we now travel to the frozen and equally hostile world of the Arctic. Here, the challenge is not just the depth, but the presence of a powerful and a destructive new enemy, the sea ice. The extreme and often sub-zero temperatures make conventional steel brittle and prone to fracture. The months of polar darkness make construction and operation incredibly difficult. But the single greatest threat is the immense and almost unstoppable force of the moving sea ice itself. To combat this, a new and even more powerful kind of fortress has been created. The great concrete gravity-based structures in the Arctic, such as the Hibernia platform off the coast of Newfoundland, are designed with a massive and serrated outer wall, a set of colossal concrete saw teeth that are designed to absorb the immense impact of a multi-million-ton iceberg and to break it apart before it can damage the platform's core. A more insidious, And an even greater threat from the ice, however, lies hidden beneath the waves. The great icebergs that drift down from the glaciers of Greenland have a deep and an unseen keel that can extend for hundreds of meters below the surface. As these giants are pushed by the ocean's currents, their keels will often scrape along the seabed, gouging a deep and a powerful trench, an event known as ice scour, which would instantly destroy any pipeline or any wellhead that was unlucky enough to be in its path. The ingenious engineering solution to this unstoppable threat is as simple as it is effective. All of the critical and irreplaceable subsea infrastructure, the wellheads and the pipeline manifolds, are placed below the level of the mudline. They are installed at the bottom of a large and pre-excavated crater in the seabed, a feature that is known in the industry as a glory hole. The top of the wellhead is now safely recessed below the seabed, allowing the keel of the great iceberg to pass harmlessly over the top of it. A brilliant and a simple solution of strategic evasion. These incredible, and often almost unbelievably audacious new technologies, from the great and silent robotic factories on the abyssal plain, to the powerful and ice-breaking concrete fortresses of the frozen north, are the essential and the enabling tools that will allow us to unlock the final and the most challenging and the most extreme frontiers of the oceanic world. They are a profound and a powerful testament to the relentless, to the adaptive, and to the ever-evolving nature of human ingenuity. We have now traveled together across the vast and the varied and the often violent landscapes of the oceanic world. We have stood on the shores and have witnessed the great war against the waves. We have journeyed out into the deep, to the silent and the lonely steel islands that stand as fortresses against the storm. We have danced with the great floating giants of the abyss, and we have followed the long and silent arteries that they have laid across the unseen ocean floor. We have drilled into the very crust of the earth from a moving platform, and we have journeyed to the final, the frozen, and the most extreme frontiers of our planet. And so, having completed this long and intricate voyage, we are left with one final and essential task. We must now pull back from the brilliant specifics of the engineering and the technology, to reflect upon the true, the lasting, and the deeply human legacy of this great and this often turbulent invasion of the sea, and what it tells us about the future of our species on this beautiful, this powerful, and this fragile blue planet. Perhaps the most profound and the most enduring legacy of our long and complex journey into the offshore world is not the immense wealth of resources that we have extracted, but the immense wealth of knowledge that we have, almost as a byproduct, gained in our relentless and economically driven quest to find and to produce energy from beneath the waves. We have been unintentionally forced to become the greatest and most systematic explorers of the deep ocean in all of human history. The insatiable demands of the offshore industry have been the primary and the powerful driver behind the revolutionary advancements in a dozen different fields of science and of technology. It was for this industry that we perfected the art of deep water robotics, that we mastered the science of dynamic satellite-based positioning, and that we developed the new and powerful materials that can withstand the crushing pressures of the abyss. And it is because of this industry that we now know more about the complex geology of our continental shelves, and about the powerful and the intricate and the life-sustaining currents of our deep oceans than we ever could have imagined just a century ago. We went in search of oil, but we found a new and a far deeper understanding of our own world. The great structures that we have built in this world will not last for an eternity. They are not the pyramids. They are complex and powerful machines, and like all machines, they have a finite lifespan, but they are, nonetheless, the great and the defining monumental works of our particular age. They are a profound and a powerful testament to the same timeless and deeply human impulse that drove the cathedral builders of the past. the desire to solve the impossible problems, to push the very boundaries of what is technologically achievable, and to impose a form of human order, of logic, and of ingenuity upon a chaotic and a powerful natural world. There is a strange and a stark and a powerful beauty in the image of a single and a lonely and a humming steel island, standing its watch in the vast and empty darkness of a stormy midnight sea. It is a symbol in its most pure and its most abstract form of the stubborn, the audacious, and the often brilliant and unyielding will of our species to build. But we must also be honest, and we must be sober in our final accounting of this legacy. Our great invasion of the sea has not been without its profound and its often tragic costs. The story of our offshore adventure is also a story of catastrophic oil spills, of the disruption of fragile marine ecosystems, and of the immense and the planet-altering carbon legacy of the fossil fuels that we have so brilliantly and so relentlessly pursued and extracted. Our relationship with the great ocean has always been a complex and a deeply fraught one. It is a story that is filled with moments of breathtaking genius and of profound courage, but it is also a story that is shadowed by moments of hubris, of greed, and of a catastrophic and a short-sighted failure to understand the full and the true consequences of our own immense and newly acquired power. And yet the tide of our history is, it now seems, beginning to turn. The final and perhaps the most hopeful part of this long story is the one that is only now just beginning to be written. The very same almost unbelievable skills, the same profound knowledge, and the same audacious and boundary-pushing engineering courage that we once used to conquer the ocean in our search for oil, are now at this very moment being repurposed and are being refocused on a new, a more sustainable, and a far more harmonious partnership with the great and powerful sea. The great and silent and gracefully turning offshore wind farms that are now rising on the horizon are the powerful and the beautiful symbols of this new and hopeful chapter. They are a testament to our ability to learn, to adapt, and to evolve. They suggest that our ultimate destiny is not to be the conquerors of the ocean, but to be its students. And they offer the profound and the hopeful promise that our future, as a species, lies not in the mastery over the forces of nature, but in our ability to finally learn how to live in a more intelligent, a more respectful, and a more enduring harmony with the immense, the powerful, the beautiful, and the life-giving blue heart of our world.